recording, Marcia? Marcia?
So I welcome everybody here again this week in online. It's a pleasure to have Professor Angela Pistoia here. She will speak on some problems of the Steklov eigenfunctions, and just to mention that she's a professor at Sapienza University of Rome in Italy, and she's, among other things, she's an expert on analysis of building phenomena in critical nonlinear elliptic problems, including Yamabe equations, Liouville equation, and Keller-Segal equations. And notably, she was the first to establish the existence of infinitely many sign-changing solutions for the renowned Yamabe equation on the sphere. This is very nice. So we're happy to have you all here. Thank you again, everybody. Keep your questions to the end. Let's get started then.
Okay, so first of all, let me thank you very much for the invitation to be here. Is a pleasure. And Marcia, let me also thank you for the nice introduction. Okay, so let me start with the talk. I will speak about some properties of the Steklov eigenfunctions, and in particular, I will speak about a couple of results I have obtained in collaboration with Alberto Enciso in Madrid, Luca Battaglia in Roma 3, and Luigi Provenzano, who is a colleague of mine in Sapienza. Okay, so the problem, the Steklov problem, what do we have? We have a compact connected Riemannian manifold of dimension n greater or equal than 2 with smooth boundary. The Steklov problem is nothing but this eigenvalue problem, this red box. I'm looking for harmonic function on the manifold M, which on the boundary was a normal derivative on the boundary is equal to sigma u. So the eigenvalues are this sigma. It is well known that they form a divergent sequence which approach plus infinity, and they can be characterized by a minimax procedure, as in the classical Dirichlet case. And the corresponding eigenfunctions form an orthogonal basis of harmonic function in the space H1M, and sigma equals 0 is simple. 0 is an eigenvalue, was corresponding eigenfunction is a constant. Okay, we take the constant one. Okay, so this is the Steklov eigenvalue problem, and there is an analogous of the Steklov problem, which can be said as the Dirichlet to Neumann map eigenvalue problem. More precisely, we can look at, okay, this in blue is the Steklov eigenvalues problem. Well, the eigenvalues can be interpreted as the eigenvalues of the Dirichlet to Neumann map, which act on the space H1 alpha of the boundary in this way. We take a function phi, defined on the boundary of the manifold. We extend in a harmonic way the functions phi on the whole manifold M, and then we take the normal derivatives of this harmonic extension. Well, this red eigenvalue problem is the Dirichlet to Neumann map eigenvalue problem. It is important to point out is that the eigenfunctions, the eigenvalues sigma of these red problems are nothing but the eigenvalues of the Steklov eigenvalues problem, the blue one. And the corresponding eigenfunctions phi k, which are defined on the boundary of the manifold, are the boundary traces of the eigenfunctions of the Steklov problem. Okay, this fact will be useful in the following. So we have two different eigenvalues problems which are closely related via this Dirichlet to Neumann map. Okay, now, which is our problem? Our problem is the following. We are interested in establishing formulas which relate the number of critical points of the eigenfunction UK with the number of critical points of its restriction to the boundary, namely the Dirichlet-Neumann eigenfunction Φk, and the topology of the manifold and of the boundary. So this is the first problem. And the second problem, we would like to count the number of nodal domains of the eigenfunction UK, and also the number of nodal domains of its restriction to the boundary, namely the eigenfunction, the number of nodal domains of the eigenfunction Φk of the Dirichlet-Neumann map. Okay, so this is our problem. And let me tell you what is known. There is an old important result by Alessandrini and Magnanini who proved the following. They gave a relation between among the number of critical points of the eigenfunction on the manifold, the number of nodal domains of the eigenfunction in the interior, and the number of nodal domains of the eigenfunctions on the boundary. So they prove this result if M is a simply connected planar domain, so a flat manifold, then there is this, they can prove this relation between the multiplicity mu k of the eigenvalue sigma k, the number of critical points, and int k, which is the number of nodal domains, and so on. So this is the list of relation that they can found. Okay, other results have been obtained by Cartole Sigillito, Karpukhin, Cocker, Poincaré-Hopf, James, and many other authors. So this is the fundamental result. Now, let me tell you what is our first result. Our first result reads as follows. We take, as a first step, we do the following. We take an harmonic function on the manifold M, and we want to count the number of critical points of this harmonic function in terms of the topology of the manifold and of something else. Let me describe what we get. So we take an harmonic function on the manifold with boundary, our manifold as a boundary, and we assume that U has isolated critical points in the manifold, its restriction to the boundary has isolated critical points on the boundary, and the gradient of this function is different from 0 on the boundary. Then we can prove this formula here. Here you see on the left, we have the sum of the index of the critical point in the interior. Okay, key of M is the Eulero characteristic of the manifold M, a topological factor, and here we with this last term count the index of the critical point of U constrained on the boundary, such that the normal derivative of this at this point is pointing inward. Okay, so this is the formula. Now let us see how we can prove the formula, and then we see how we can apply this formula to get to count the number of critical points. So first of all, which is the main tool? The main tool is the Poincaré-Hopf theorem. Everybody knows this theorem. It tells the following. We have a Riemannian manifold, and we take a vector field V, which is isolated zeros on the manifold. Well, if M has a boundary, we assume that the field is pointing inward on the boundary. I mean, this green condition holds. Nu is the outward normal. Okay, so what is important is that the component of the field along the normal is different from 0. then this red formula holds true. What does it mean? It means that the Eulero characteristic of the manifold is equal to the sum of the index of the field V at the point where it is 0. What is the index? Okay, so this Poincaré-Hopf theorem gives a relation between a topological factor, which is the Eulero characteristic of the manifold, and some analytic factor, which is the sum of this index. Let me tell you what is an index. Maybe you know, but maybe there are some young people here. Let me recall. In particular, we will use the Poincaré-Hopf theorem when V is a conservative field. It means that V is the gradient of a function f, defined on the manifold M. Well, if x, the critical point of f are the zeros of the potential V. Well, if x is a non-degenerate critical point of f, of the function f, it means that the Hessian matrix is not singular, then the index of the gradient of f at the point x is equal to -1 to the m of x, where m of x is the Morse index of the critical point x. What is the Morse index? Is the number of negative eigenvalues of the Hessian matrix. Well, in general, if x is a minimum point, the Morse index is 0 and the index is equal to +1. If x is a maximum point, the Morse index is equal to the dimension of the manifold n, and the index is -1 to the power n. Let me stress this, let me highlight this fact. If the manifold is a surface, is a two-dimensional manifold, well, if I have a minimum or a maximum point, well, the index of the gradient of f is equal to +1. While if I have a saddle point, the Morse index is equal to 1, and the index is equal to -1. So in a surface, I can only have critical points whose index is +1, which are minima or maxima, and critical points, which are saddle points, whose index is equal to -1. Okay, this is the starting point. Now let us see how we can prove our result. Our result is this one, this formula. Okay, now let us prove the result. This is very easy. Indeed, what we do is the following. We take here the manifold with the boundary. This red guy here is the boundary of the manifold. What we do, we double the manifold and we glue the manifold, and we do, okay, we have M, we double, we make a copy of M, and then we glue the two manifolds along the boundary, and we get a new manifold, which is the double, the M, which is a new manifold without boundary. Now what do we do? Remember that we have an harmonic function U. We build a function U tilde defined on the whole manifold M in this way. The function U tilde coincides with U on both copies of M. But now this U tilde is not regular on the boundary, because I take the copy, okay? But then what happens on the boundary? What do we do here is the following. We change a bit the function U tilde in a blue neighborhood of the boundary, so that the new function is smooth. And the new function is smooth and coincide with the initial function U on the boundary M of M, this red boundary. Then it is possible to choose the size of the tubular neighborhood small enough so that the critical points of U tilde in this blue region are only on the boundary and don't produce any other critical points. And it means that the critical points of U tilde correspond exactly to the critical points of the hold U, of the initial U on the boundary. And this is possible because we assume that the gradient of U is different from 0 on the boundary. Normally, what happens? How many critical points have this new function U tilde? Well, the function U tilde, which is smooth now, has the critical points of U counted twice and the critical points of U on the boundary of the manifold M. And all these critical points are isolated by assumption because I want to apply the Poincaré-Hopf theorem. And now I apply the Poincaré-Hopf theorem to the manifold Dm, which is this new manifold I have obtained by gluing the two manifolds. And what I do is the following. This manifold, this double manifold does not have any boundary, so I apply the Poincaré-Hopf theorem this way. The Euler characteristic of the M is equal to what? I have to take the sum of the index of all the critical points. So I have 2 times the index of a critical point of the U inside M, plus this blue guy here, which are the critical point, the index of the critical points on the boundary, of U tilde on the boundary. Now, what we have to do, we need to compute the index of the gradient of U tilde at the points on the boundary. But now, when I have U and I double U, what I do is the following. It is like I have U on the one side, I have U on the other side, and I glue. So you see that if the normal derivative is positive, this critical point, this X, is a maximum along the normal direction because I'm gluing. So I take U here, U here, U on the other side. And if the normal derivative is positive, this X is a maximum. And so the index of the gradient of U tilde is minus the index of the gradient of U on the boundary. And if the normal derivative is negative, I have the same, I mean, U tilde, this X is a minimum of U tilde along the normal direction, and the index of the gradient of U tilde is equal to the index of the gradient of U restricted on the boundary. Then I can compute this blue sum in this way. I have to distinguish the two cases. And then finally what I do, I take the restriction of U on the boundary and I apply the Poincaré-Hopf theorem on the boundary. Okay, so I write the Poincaré-Hopf theorem on the boundary, applied it to the restriction of U on the boundary itself. Then I use the additivity properties of the Euler characteristic, I cook all together and I get my formula. Okay, so this is the idea. Now, what we get, so is the theorem. I take an harmonic function which has isolated critical points such that its restriction to the boundary has isolated critical points on the boundary. The gradient of U is different from 0. I have this formula. Now, I want to apply this formula to the Steklov eigenfunction. Because here you see in this formula, the sign of the normal derivatives of U on the boundary plays a role. But now if I take the Steklov eigenfunctions, you see that the sign of the normal derivative is nothing but the sign of U on the boundary. So if I apply this formula, I can write this green term here in terms of the sign of U on the boundary. And again, what I do is the following. Now I am counting the index where u is negative. So what I do, I take the points, the nodal region on the boundary where u is negative, and I apply again the Poincaré-Hopf theorem to this to the restriction u on the boundary on this manifold. I make this computation. Now the nodal region of u on the boundary can be the union of some connected components pi. Again, I use the additivity properties of the Eulero characteristic, and I get this formula here. Okay, I write here, sorry. Okay, I write it, I have this formula. And so finally, what I have is the following. Now, I take an eigenfunction of the Steklov, an eigenfunction of the Steklov problem, assume that the eigenfunction has these green properties, then I have this formula. Here you see what we have. We have that the sum of the index of the gradient of the at the critical point is equal to the Eulero characteristic of the manifold minus the sum of what? Of the Eulero characteristic of the disjoint component of the set where u is negative. So you can see that this formula claims a relation between critical points and a topology of the manifold and the topology of the boundary set where u is negative. Now, let us see if this gives you, it allows us to count the number of critical points, because up to now this is not possible. But now we use the remark I made at the beginning, and assume that the manifold is a surface, okay? So I want to apply this formula to the case when M is a surface. Now, let us start with this green term. Now, this green term gives you, what do we do? We take the boundary of the surface. The boundary of a surface is a curve, or a disjoint union of curves. Then I take the set where u is negative, the nodal domain where u is negative, and u, this set, is the union of intervals or simple closed curves. If the pi is an interval, the Eulero characteristic is equal to 1. If the pi is a simple closed curve, the Eulero characteristic is 0. So this green sum can be written in this way. Is the sum of Lj when j is equal 1 to L, and L is the number of connected components of the boundary where u changes sign. And Lj is alpha of the number of nodal domains in the j's component. I will give you a picture in the next slide. So this green terms is clear. Now, let us compute this red term. The blue term is the Eulero characteristic of the surface. Now, this red term, if u is an harmonic function, all the critical points in the interior are saddles. They cannot be minima, neither maxima, because the Laplacian of u at the critical point has to be 0. So the Hessian has to be two different, cannot be positively definite or negatively definite. It has to change sign. So all the critical points are saddles, and the saddles have a Morse index equal 1 on the surface. The surface has dimension 2. And so I can write this red sum in this way. So the index of the gradient at the critical point is -1 up to the Morse index, and -1 to the Morse index is -1, sorry, is 1. No, sorry, this is -1. And so here what I get is minus the number of critical points. And so finally, this formula reads in this way. The number of critical points of the eigenfunction is equal to this green term, which is related to the boundary, and this blue term, which is the Euler characteristic of the manifold. Now, let me give you an example. Assume this the M is like this one. And in this case, this is a surface. I am considering the case where M is flat, okay? So an open domain in R2 with boundary. So in this case, the Euler characteristic is 1. Assume that the eigenfunction changes sign exactly twice on the boundary. So this manifold, this surface has only one component of the boundary. There is only one boundary component. The eigenfunction changes sign exactly twice. So capital L, small l is equal 1. I put all these ingredients here, and I get that U has a 0 critical point. Now, if the eigenfunction changes sign more than twice, in this case, for example, we have 4 nodal regions on the boundary, 1 here, 2 here, 3, 4, then I have that L is equal to. And so I put all this data in the formula, and I get that U has a 1 critical point inside the surface. Here I have another situation where on the boundary I have I have 6 nodal regions. I take the alpha, which is 3, I put here, and I get 2 critical points. And I can do also when I have the boundary. For example, when the surface has 2 different boundaries, for example, it is like an annulus. Here, the Euler characteristic is 0. There is a component of the boundary where the eigenfunction changes sign exactly twice. I put all the ingredients here, and I get that there is 1 critical point, and so on. So the idea is this one. So this formula here allows us to count the critical points. Now, I don't remember at what time I have to finish in 20 minutes. I don't remember, sorry.
You have 10 to 15 more minutes.
10 minutes.
10 to 15, yes, you started, yes.
Okay, 15, okay, thank you. Okay, so this is the formula. Now there are these here. I am to make some remarks on the assumptions, because here we need to assume, to get our result, we need to assume that the Steklov eigenfunction U must satisfy this green hypothesis. We cannot expect that this always hold for non-constant Steklov eigenfunctions, but it is reasonable to expect that they hold for generic metric. What does it mean? It means that I have a manifold with a metric G, then I can always find a metric G tilde close to G, such that all these green assumptions are satisfied. And this can be done using a transversality argument like the one used by Uhlenbeck in an old paper. So what we can do is that for a residual set of matrix G, all the non-constant Steklov eigenfunctions are Morse functions on the manifold M. And let me tell you that there was a previous result due to Wang, where he proved that there exists a residual set of Riemannian matrix for which all the Steklov eigenvalues are simple. This is in the Uhlenbeck spirit. all the non-constant Dirichlet omega eigenfunctions are Morse, it means that the Steklov eigenfunctions restricted on the boundary are Morse function, and also that 0 is a regular value on the boundary. So these are the ingredients we need to state our result. Okay. So now let me tell you that this is the result. So for generic metric, we can, for generic metrics on the surface, we can count the number of critical points. But let me make a simple remark. What happens in the case of the disk? In the case of the disk, all the generic properties fails to, they're not true anymore because the disk has too many symmetries. And indeed, in the case of the disk, which is the worst case, we know that this is the sequence of the eigenvalue. There are the corresponding eigenfunction which can be written directly, that they are this one. And all the eigenfunctions cannot be Morse because the origin is a degenerate critical point. However, the second eigenfunctions, this one, r sin theta and r cos theta, are Morse function. And they do not have any singular zeros. So it suggests that in the worst case, the case of the disk, the second eigenfunctions has all the properties we use to count the number of interior critical points. And indeed, what we prove is that this is not only true for the disk, but our formula also true for any surface of genus 0, because we can prove that any surface of genus 0 is such that the second eigenfunctions are Morse function. They do not have any singular zeros in the interior, and the singular zeros, if exist, are non-degenerate. And moreover, if the manifold is simply connected, then there are no singular zeros on the manifold. Well, using these properties, we can prove that our formula holds true for the second eigenvalue. So on a surface so we take a surface of genus 0, we take the second eigenfunctions of this of the Steklov problem on this surface, and then we can apply the formula to count the number of critical points. In particular, if I apply this formula to a simply connected planar domain, we recover the beautiful result by Penn and Philippin of many years ago, where they proved that the second eigenfunction does not have an interior critical points. We extend this result to a surface of genus 0. Okay, now let me go quickly to the second problem, which is the following. The original purpose of our job was to try to recover some information about the number of nodal domains of the eigenfunctions restricted on the boundary in dimension greater or equal than 3. In particular, there was an open question arised by Girouard, Polterovich, Kolboy, Girouard, Gordon, and Scher, where the question was the following. Can a second Steklov eigenfunction have an arbitrary number of boundary nodal domains in dimension greater or equal than 3? More generally, can we have a current type theorem for the Dirichlet-Neumann eigenfunctions? Well, let me tell you that, okay, this is the usual current theorem for the Dirichlet eigenvalue problem. The number of nodal domains of the eigenfunction of the Dirichlet problem is greater or equal than k, where k is the eigenfunction uk the k associated with the eigenvalue lambda k. Okay. Now this proof, I go fast. Now we take the Steklov eigenfunction, the UK Steklov eigenfunction. It is true that the number of nodal domains in the interior of the manifold is less or equal than k. So the current theorem still holds true. But what can we say about the number of nodal domains of the restriction on the boundary? Okay, can we say that okay, the number of interior nodal domains is less or equal than k if I take the eigenfunction uk. But can also we say that the number of boundary nodal domains of the function uk is less or equal than k? Well, the classical arguments which use a variational characterization of the eigenvalues, the maximum principle, and most of all the unique continuation property cannot be applied, do not work. And indeed, it is possible to prove that using the Alessandrini-Magnanini theorem I stated at the beginning of the talk, together with some other result, it is possible to prove that if my surface is simply connected, then we have this blue estimate. The number of boundary nodal domain is less or equal to 2 times k minus 1. K is related to the eigenvalue lambda k. Okay. Now, what can we say about in 3-dimensional? Look, this result is true for a surface, so for a manifold of dimension 2. Now, what happens when I have a manifold dimension greater or equal than 3? And there is a beautiful picture, which is this one in the paper by Giroux, Polterovich, Golbois, Girard, Gordon, and Scher, which is the following. Now, in this picture can be read in this way. This green big set is the manifold, okay? The manifold with boundary. Inside the manifold, I have an hypersurface, an orange hypersurface. And the question is, can this hypersurface be the nodal set of the second Steklov eigenfunction? Look, the number, if the second eigenfunction has this nodal set, it means that the number of interior nodal domains is 2, one inside the orange region and one outside the orange region, but the number of boundary nodal domains is arbitrarily large because there are this part here, you see? Well, is it possible to have this kind of situation? Well, here we have the second result, which has been obtained in collaboration with Alberto Inciso and Luigi Provenzano, which tells you that this is possible. I mean that we take a compact manifold with boundary dimension greater or equal than 3. Then for any s, for any integer s, I can find a metric on the manifold such that the second eigenvalue is simple and the second eigenfunction has exactly s nodal components. It means that the number of boundary region, of nodal boundary region is equal to S. More generally, for any integer k and s, I can find a metric for which the first k eigenfunctions, eigenvalues are simple, and the number of nodal domains is greater or equal than S. So it is as large as we want. And so the current theorem for the Dirichlet-Neumann eigenfunction does not hold. Let me tell you very briefly how it can be proved, just the idea, because this is very simple to be said. What we proved with Alberto and Luigi was the following. Let us consider the manifold M, and inside the manifold an hypersurface sigma, which separates the manifold in two connected components, one inside, one outside, and assume that there is this condition of transversality. Well, for an integer k, I can find a metric on M for which the first k eigenvalues are simple, and such that the corresponding eigenfunction uk as a nodal component is isotopic to sigma. So let me tell you how we build the just a couple of minutes, how we build the example. So this green surface is M, is the manifold with boundary. Inside we have sigma, the hypersurface. We have inside sigma, outside sigma. Then we take a tubular neighborhood of sigma, this omega. And this is diffeomorphic to this product. When t is equal to 0, we have exactly sigma. So we move along the normal derivative. Okay. Then we choose a metric on sigma, and we choose a small number beta, and we choose on omega, this tubular neighborhood of sigma, a metric g beta, which is the product, which is the pullback of this, the product metric dt square plus beta square h. H is a given metric on sigma, beta will be very, very small, dt is the metric on the interval. Then what we do is the following. Look what happens. We consider a metric which is discontinuous, but this is not important. We can smooth this metric, which is this metric, this blue metric on G, on the omega, in the neighborhood of my manifold, or my hypersurface, and the epsilon square G, very small, far away from the tubular neighborhood. Look, omega is the tubular neighborhood of sigma. Then what do? We want to look at the Steklov eigenvalues. It means that I have to take this Rayleigh quotient, okay? The Rayleigh quotient related to this metric. This metric is made by two parts. One part is in omega, the blue part, and one part is very small. It is far away from omega. I write the Rayleigh quotient with this metric, and see, look what happens. When I take this small metric here and I compute the gradient in this metric, here I have a quantity epsilon n minus 2, which when n is greater or equal than 3 and epsilon goes to 0, disappears. And the same happens also below. Okay, so if, roughly speaking, I take the Rayleigh quotient, which gives you the Steklov eigenvalues, and I take the limit as epsilon goes to 0, what I get is a new Rayleigh quotient, which is related to the eigenvalue problem of this sloshing problem. And this is a sloshing problem, which is very interesting when you work in fluid dynamics. But in any case, what you see is that this red Rayleigh quotient gives you the eigenvalue of this problem. Here I take an harmonic function in omega, in the neighborhood of my sigma, on this green part, which are the parts where the sigma touches the boundary of the manifold, where I want to see what is important. Okay, this green part here, and there is this lateral part where so on the green part I have the Neumann, the Steklov condition, and on the lateral part I have the Neumann condition. Then what I do, we study the eigenvalues of this problem. And we prove that when epsilon is small, beta is small, all the eigenvalues of this problem are simple, and the associated eigenfunction have a nodal component which looks like exactly sigma. In particular, the second component has only one nodal component. Okay, so this is the final step. I can take the metric is discontinuous, but we can take it in a continuous way. And finally, and so this is the idea, okay? Now I don't have time to go into the details, but the idea is to pass to the limit to get this Loschin problem, and then I get what I want. Finally, okay, so the current theorem does not hold for the Dirichlet normal eigenfunction. Indeed, for an integer, what we proved was the following. For any integer, I can find a metric for which the number of boundary components of the associated eigenfunction is larger as I want, is as large as I want. But now, this fact does not rule out the possibilities that as k goes to plus infinity, a sort of boundedness is true in this way. Why should it could be true? Because as k goes to plus infinity, the Dirichlet normal eigenfunctions look like the eigenfunction of the Laplacian on the boundary, for which the current theorem holds true. Okay, I'm sorry, maybe I was too fast, but muito obrigada, and thank you very much for being here.
Thank you, Professor Pistoia. Do you have any questions? I enjoyed the talk very much, and I was going to ask you about the difference between the Dirichlet problem, and in the end you were elucidating my doubt. I would like to know if you have a particular geometric setting where the Steklov eigenfunctions would behave badly or have an unexpected behavior or something.
No.
No.
I don't know. No, indeed, what we see in our example, we have the manifold and we build a metric which is very bad. This is a very bad metric. Because you see, because the metric is zero everywhere except along this surface where I want that my eigenfunction have to be the nodal region. So this is, but in general, it is not possible given a manifold with, or even a domain, maybe in a domain is even worse, given a domain which is not a cylinder, a disk, a cylinder, or something special, it is very difficult to check what is going on.
Okay.
I don't know if I answered to your question, Martin.
Yeah, and also in this regard, what would be your next step concerning geometric situations, and or you said that you were going to the three-dimensional things to see what's going on, but any insights or any direction?
I would like to see, here you see we build the metric. What I would like to know if it is possible to do something similar but in the Euclidean setting. I mean, I have my domain omega, and to see if I can perturb the domain so that what it is expected can be proved, but without building the metric. So in the Euclidean setting, I have the domain. I would like to play with the geometry, with the topology of the domain, to see if it is possible to find this kind of result. But it seems very, very difficult. I have no idea at the present.
And are there numerical methods to approximate either the eigenvalues or things like that?
That's a very good question. I'm not an expert at all in this kind of approach, but I think this is very, very useful. If it would be possible to study using a numerical approach, because the numerical approach gives you the idea of what it is going on. But unfortunately, I'm not expert. I'm not expert. I would like to be expert. I mean, it is
Neither
a
do I.
powerful, very powerful tool. No,
Yes,
I agree with you.
To give you insights for the.
Absolutely.
Thank you very much for your nice talk. I loved it, and the pictures, they help a lot to understand what's going on. Thank you very much, guys. For next talk on April 16, we'll have two outstanding speakers.